42. And now we want this to equal 1. So we want to normalize. All right? But now, why do we want this? Why do we want to change our wave function, put something in front of it to have this all add up to 1? This is awkward. This is very awkward. I'm presenting this awkwardly. I apologize, but it's all cool. Because ultimately, I want the wave function squared to be the probability density when I add up all the probabilities and want it to come up to 1. So right now, psi is not a good candidate for the probabilistic interpretation of the wave function. Okay, so let's start there. Let's go back here. Why is this psi not a good candidate for the probabilistic interpretation of the wave function, as it is right here? So why is this statement true? Why is it a horrible wave function for the probabilistic interpretation?
Because it's not equal to 1?
Because when you add up all the probabilities, it adds up to 42. Probabilities don't add up to 42. Probabilities go 0 to 1. Okay, so that's a bad candidate.
It's not a real-life interpretation.
What's that?
It's not a real-life interpretation.
Probabilities don't show up greater than 1, right? Yeah, so it doesn't give you a world. All right? So how can I make it better? How can I make psi work? And the answer is normalize it. Okay? So how can I make that psi work? And I want to normalize it. So what I'm going to do to normalize it, I'm going to throw a constant in front of the wave function. Alright? Now, the reason I started over here is because what happens when you throw a constant in front of the wave function for all observables, like position and momentum? It does nothing. Alright? It doesn't affect it. So I'm free to throw this constant in front of it. That's called my normalization constant. Right? Okay. Then, what am I going to ask to make it work quantum mechanically? So for my new wave function to work quantum mechanically, right, I need to have psi, my new wave function, psi star, if you want prime, so this is psi prime star psi dx equal 1. That gives me a good working wave function. Why is that a good working wave function?
Because normalized, you take that end out of the equation and then...
Well, too complicated. Because when you integrate the probability density over all the distance, you equal 1, right? So does this, if I can find this n that makes this equal to 1, have I turned it into a good probability density? And the answer is yes, and that's what's called normalization. Okay, so now watch. When you solve this, we're going to get the same thing I had before. You pull out an n squared. This is not a complex number, so you pull out an n. So it's minus infinity to plus infinity, a regular psi star, psi dx, and you set that equal to 1. So that n squared equals 1 over the square root of the integral from minus infinity to plus infinity, psi star, psi dx. And what does that equal to?
42. 1 over square root of 42.
1 over the square root of 40. So what that implies, it implies that n, so solving for n. So that implies that n equals 1 over the square root of 42.
Yeah, not n squared.
Okay? Everybody okay? Okay, I admit that was the worst approach, or one of the most horrible approaches I've ever done. It was not clean, it was not good. All right? But in the end, I think this discussion came out okay. All right, with the idea of how to normalize. So now, what is my wave function, guys? So what is my good quantum mechanical wave function? It is psi equals, what's in front here?
1 over the square root of 42.
1 over the square root of 42 times my old psi, if you want. That is a good wave. That is a normalized wave function.
So why do you need to normalize? Like, you need to normalize it because...
This is a question you should be asking.
Yeah.
So keep going.
Okay, like, in this case, you get to normalize it because the probability equal 42,
Right.
and it can't equal 42.
What do probabilities have to add up to?
It has to be less than 1.
Okay.
One or less than 1.
Well, individual probabilities have to be
Oh,
less than
yeah.
1, but when I add them all up, they have to equal 1. So what is the process of normalization is?
You get
Okay, it's equal 1.
Yeah, getting all the probabilities to equal 1.
It's really just finding a constant, like that, finding n pretty much.
It is called, it's n is n for normalization constant.
Okay.
Yeah. All right.
So we can force it to be a W.
So you're forcing it to be interpreted as that probabilistic interpretation of the wave function. What is the wave function? I don't know. But I know the integral of, the probability density over all space has to equal 1.
Good question. Is n always going to be 1 over the square root of what number you're trying to get rid of? Because in this case we said equals 42, so n want to be 1 over the square root of that.
Yeah.
Is it always going to be that?
Yeah, so whatever this...
Be that then?
Yeah, okay. But now here's a bigger point, and this is the footnote Dale was talking about. So what at least candidate functions are good for possible wave functions? How about this? So what functions might be possible wave functions that represent reality? Whereas reality is when you add up all the probabilities, it adds up to 1. The answer is all wave functions, right? That if you go psi star psi dx, and they come out to be finite, right? Do those have a chance of being a good quantum mechanical wave function?
Yeah, because we can just normalize it.
Because you can normalize them. That's it. So this is kind of good. This actually kind of came around to be pretty good. All right? Here's the scoop. Wave functions that satisfy this are called square
Integrable.
normalizable or integral. Or square integrable. I think it's really square integrable, as you said.
I just heard that somewhere.
Yeah, I'm sure I said it before. I don't know why I said normalized. Yep.
Page 14 in Griffith's.
Yep.
Griffith states that psi is normalized at t equals 0.
Yeah. This is funny. The way you said that, Mike, it reminded me in church. You said like page 14, and then I heard all these books go to page 14. Right? And then you picked out a place inside, and you go, and Griffith said.
Yeah.
I mean, I don't care what it is.
It's going to state Maxwell's equation. And it was like,
It was really funky.
Yeah. What it was like.
Yeah.
And, Jay Towell once joked around and said, this is the stuff that needs to be chosen on a tablet.
Yeah, I agree.
So,
Yeah.
funny little-
He made it into a tattoo, anyway.
He did.
Yeah.
So it says if psi is normalized at t equals 0,
Yeah,
it stays normalized for all future time.
yeah, yeah.
So
So you guys should go through that argument and make sure you can do that.
Well, when it says it stays normalized, we're all.
So what does that mean? So the next page, Mike has pointed out, and I still want to get to Dale's comment, is that once you would normalize the wave function, that it stays normalized, and it's a solution to Schrodinger's equation. So square normalizable functions, so they got to be square normalizable functions, all right? And they also have to be solutions to Schrodinger's equation. I usually start with, this is the way it's done most commonly. You look for solutions to Schrodinger's equation. There might be a million or an infinite number of them, right? Which ones of those are you going to choose to represent reality?
Whichever one's square and normalized.
Only those that are square integrable. The others, what do you say? They're solutions, but they don't work. Okay? Now, square integrable solutions to Schrodinger's equations, the normalization stays constant as a function of time. And on page 14, Griffith demonstrates the proof of that.
Right.
All right? Now, look at what would happen if that wasn't the case. What would happen if normalization didn't stay constant with time? What it would mean about the probability, the overall probability?
It would change as a function.
That the probability, if you integrate it from minus infinity to plus infinity, could be different from 1.
So they're feedbacked into another.
What's
The
that?
wave function is conserved too?
Say that again, please.
So does this mean the wave function is conserved and there's a symmetry involved?
Yeah, well,
I mean, certainly the wave function can change as a function of time, and wave function does change as a function of time, and what we're going to be interesting is building up solutions that are sums of wave functions, and when you sum up wave functions, you get very interesting, time-like behavior. All right?
but wasn't the, I think I remember reading something about it showing like the classical wave function where it's just x minus vt and saying that the wave stays the same, it just, the position changes with time. Like it,
Yeah,
that's the way it would
but
look.
that would be like some type of stationary solution where the solution looks the same as a function of time. All right?
Right, well, that's what I'm saying. That would work with that definition because as you change t, you normalize it once. It's you've got the wave.
Most definitely. What we're doing, chapter 2 starts off with time-independent stationary solutions. All right? But the real life gets more complicated. They get to be sums of stationary solutions, and they have very definite time-dependent things that look different from
Well,
those.
yeah, if you had, that's what I'm saying. You mentioned that if you had two different waves that are two different frequencies, you add them together,
They
you're going
look
to get an
different.
interference
Yeah.
pattern.
Okay? So, the big kicker there, Mike, I think to take away is that you can show, and he shows it, and go through the arguments. He uses Schrodinger's equation again to solve it. You should prove it to yourself. But the point is that once you've done this, you've found a wave function that adds up to probability of 1. Then for all of time, the probability adds up to 1. All right? And so you're okay.
Did you say wave function?
Wave functions very definitely have a time dependent.
So couldn't a wave function change to eventually?
Okay, here's what I want you to do. Before you go any further, do that proof.
All right.
All right?
Okay.
And that's where your answer is going to come. Okay. So square integral, and this gets confused, okay? Square integral solution. So what we do is we solve Schrodinger's equation. Solve Schrodinger's. And of all the answers, of all solutions, we take only square integrable solutions. And the reason is for everything we just did.